Just imagine for a second, you are a data scientist and a company approaches you and they give you their data. Okay. And the data is on sales and advertising budget on different medias. Okay. And your job is to give them the insights from the data so that they can increase their sales. Okay. On the given past records. Okay. And guess what happens when you see the data? You get mesmerized and you terribly fail at giving them their insights, because when you open the data and you see the data, you see this is not what I have seen in my whole life. This is not what my 200 online courses had taught me. This is not a YouTube tutorial data. It is actually real data, real ugly raw data. Okay, you terribly fail at it, and guess what? The company ditches you. Okay, they ghost you, and at last they dump you. So, what's the conclusion? Nothing, just focus it. Okay, hey everyone, this is statistical learning. Okay, so what your job was? Your job was to simply give them the insight number wise so that they can increase their sales. Okay, so the medias on which they were spending their budget was radio, TV, and newspaper. Okay, so what you had to do? You simply had to find that on which or how much should they spend to increase their sales. Okay, so our goal was to develop accurate model. Okay, our goal is to develop accurate model which is used to predict sales on the basis of the three media budgets. Okay, so let's see what we can do. So we have to first agree these things, that we have a input variable, we have a output variable. Okay, input variables are media, which is TV, newspaper, radio, and the output variable is sales, because we have to get better at sales. Okay, we have to increase the sales. So we come to a conclusion and we find a magical thing, which is y equal to fx, in which y is the sales. Okay, this is the sales, and it is affected by the budget of these three medias. And what this f here is, so f is a function which estimates, okay, which gives the estimation of the sales, which gives the estimation of the sales based on these media. Okay, so we have to find f. What is f? We have to find it, because if we find f, we will simply can get the sales increased. Simple man. Okay, so why should we estimate f? Why should we even think of that thing, that why should we estimate f? Cannot we just get some numbers randomly from the data and we just simply put and we can get the sales and all this thing, like solving a Rubik's cube where you fail, learn, fail, learn, fail, learn? No, we need a systematic approach. We actually need a algorithmic way or systemic or step-by-step approach so that we can increase it. Okay, so estimating f. Why do we estimate f? So for two things. Number one is prediction and number two is inference. So if we want to predict, okay, based on the budget or different medias, okay, or using some different time or subgroups or anything. So if we want to make prediction, okay, so if we estimate f, we can definitely make prediction on the new data. Okay, because the customer will increase and they'll get their data and they can be recorded and we can make prediction more and we can increase the sale. Or second, what we can do is that inference, in which we understand the association, the relationship between X and Y, which is the sales and the media, okay, which is the input variable and the output variable, the relationship between input and the output variable. For example, which predictor are most associated with response, which simply means that which affects the sales more, okay, or which affects the response variable more, the y more. Okay, the relationship between predictor and response variable. Okay, what is it? Is positive, it is negative, it is um, nothing, or it is highly correlated or highly negative, or what? Okay, or can relationship be summarized by a linear relationship, or is it more complex, or is it quadratic, or is it, what you can say, it is not linear, it is declining. Okay, is it linear, it is declining, it is quadratic, it is exponential, it is exponential, what it is? So for inference, we estimate f. Okay, the two things, prediction and inference. Now the question arises, how do we even estimate f? How do we even estimate f? So estimating f, okay, estimating f should result into y. Okay, our goal is to find a function f such that it approximates to the y. It approximates to the y. Okay, now there are two methods. There are two methods that are useful. Number one is parametric methods. Okay, so in parametric methods, what we do is that we make an assumption about the form of x. Okay, so we assume, we haven't seen the data yet, but we assume that the relationship, okay, that f makes with y is linear, is linear. Okay, so if the budget increases, sales increases. This is our assumption, not the data. Okay, this is not based on data, this is our assumption. And what we do is that inside the x, we create this formula, we create this equation, or the formula, the equation, and we get to the conclusion, okay, of this equation. Okay, the model has been selected which is linear, and we fit the model using the training data. Most common of this is called ordinary least squares. Okay, this is called ordinary least squares. Okay, now the problem of estimating f reduced to problem of estimating a set of parameters. Okay, now, so earlier we had to estimate f such that it can be approximate to the y, which means that we have to find the relationship so that we can get the sales. Okay, now we have to just find some parameters to find f, which means to find sales. Okay, now we have discussed the first method. Now the second method, which is non-parametric method, in which we don't make any assumption. We try to estimate f which that gets as close to the data point as possible. So here we do not make any assumption, we do not take any relation, we do not take any equation, but we assume and we try to figure out as much data as we can. We can figure it even linear, we can, it can be quadratic, or you can say u-shaped, or it can be uh, declining or negative relationship. Okay, it is linear, but it is declining, in which we need large amount of data. We need large amount of set of parameters to find these values. Okay, and this could be a way. This could be a way. So we we can estimate f by using parameters, parametric way and non-parametric way. Okay, now the second thing, after we choose the parametric or non-parametric way, we have prediction accuracy and model interpretability. Model interpretability. Okay, so the two terms, we have two terms, interpretable and flexible. Okay, so we say a model is interpretable in a way when we understand how it makes the prediction. Okay, how it makes the prediction, the easier it is to understand. Okay, easier to understand how model makes prediction. Okay, how it predicts, the more interpretable it is. Okay, if we understand how model makes prediction, it is interpretable. So flexible means how complex relationship it can understand. Okay, how much complexity it can handle. The more complexity it can handle, the more flexible it is. The more flexible it is and less interpretable, because the more the complexity, the less it is easier to understand. Okay, it is very hard to understand. Okay, so two terms, interpretability and flexibility. These two terms are very important, because as the interpretability increases, the flexibility of the model decreases. Okay, the easier to understand the model, the harder, okay, the harder it is that it can understand the complex relationship. Okay, now what does complex relationship mean? Um, you can simply say which is non-linear. Okay, all the data which are non-linear, which means they do not form this pattern. They do not form this pattern in a way that if my budget is increasing, then my sales is also increasing. No, that doesn't make this come true. Okay, so if the data is non-linear, if the relationship between the predictor and response is non-linear, it is complex, which means non-linear. Okay, that is it. And if the model is complex, we use flexibility. And if the flexibility in the model increases, interpretability decreases. Okay, as you can see, as the interpretability increases. Okay, as the interpretability increases, the flexibility decreases, and as the flexibility increases, the interpretability, okay, or the way so that we can understand the model, how easy we can understand the model, decreases. Linear regression, KNN, and all these simple models that can be understood very easily on the paper, and we can show that how it make prediction. Okay, the more interpretable it is. But if we cannot, like on the paper we can say that, but in general we cannot actually understand on paper that how it makes prediction. It is not that easy to say how it made the prediction or how it came to the conclusion. Okay, that where flexibility comes in. That's the term that we use. The more complex the model uh, can be, the more flexible it is. Okay, so simply you can say flexibility, complexity. Okay, the more complexity, the more flexibility, or the less complexity, more interpretability. Simple as that. Okay, now restrictive models are usually more interpretable, so useful for inference. Okay, so if you want to know the relationship or want to get better at uh, the data, or how it association between variables and predictors and response variables, then we can use interpretable model, because it is easier to understand, like linear regression. Okay, it is very interpretable, it is very easy to understand that how it make predictions. Okay, it uses simple equation in which we find parameters and we fit the parameters, then we estimate it, then we measure it, and we get to the conclusion. That is it. So if we want to understand the inference, then we use a more interpretable models. Okay. Now, flexible model can be difficult to interpret due to complexity of F. Okay. So the more, as I have told earlier, that the more complex F would be, the harder it is to understand, and the harder it is to understand, the more complex it is. Okay. That is it, which means the relationship is complex. Okay. We have fit the F, we have choose parametric or non-parametric. Now we have choose that, do we have to make prediction or do we have to do the inference? Okay, we have chosen one. Now we have to assess model accuracy, that how well the model is doing. If it is not, then there is a problem, we have to fix it. Okay, so there is no any single best statistical approach to find how well a model is doing. We just pick one method and we use it, and we try to minimize the error or minimize its error rate, and we increase its performance. Okay, so the commonly used measure that we use mostly is mean squared error, MSE. Okay, MSE. I hope you would have heard about this thing. What we do is that we take our real value, okay, the ground truth, the real value, and we compare it with our predicted value, the predicted value, and then we see how much different is there between them. And then we square it and we take average of it. And the more it is, the more MSE is, the bad model is. Okay, the bad model is. And the less MSE is, the more the good model is. Okay. Okay. So we have some graph here. Okay. We have some graph here which tells us how good our model is based on their interpretability and flexibility. Okay. So in this graph, okay, in this graph, the X and Y, okay, we can see that there is a linear relationship. There is a linear relationship. We can say that because as the X increasing, as the X increasing, Y is also increasing. Y is also increasing. Okay. And now we have different approaches. Okay. We have different approaches. Number one is this black line. Okay. This black line, you can see this black line, which is which is showing a linear relation, which is showing a linear path. Okay, which is showing a linear path. Now there is this green model. Okay, this there is green model which is trying to capture every move, which is trying to capture every noise. Okay, and there is a yellow. You can see here there is a yellow line between the data. Okay, there is a yellow line between the data, which is doing what? Which is also showing a linear line. Okay. Now, here we have flexibility. We have flexibility and mean squared error. Okay, as I have told, the lower mean square error is, the good our model is, and the more MSE is, mean squared error is, the bad our model is. Okay, so we have the mean squared error and we have 1. Okay, so 1 is like good measure, but so what we can see here is, okay, so these two are, this is test and this is train. This is train. Okay, so this is training MSE and this is testing MSE. So what matters more is that testing and training MSE's trade-off. Okay, so if we see the yellow line, okay, yellow line, which is showing a linear line, which is showing a linear line, the yellow model. So in the training and in the test, it is giving around 0, nearly 1, not 0, but nearly 1. The MSE is nearly 1, which is a very good thing because this is a minimum error. But we want minimum error, so we'll explore more models. We'll explore more model so we can get even, less. We can get even less error. Okay, if we see blue. Okay, if we see blue model, what it is doing, so we can, you can simply see is that it is lower than the yellow. The blue is lower than yellow, which means the test MSE error is lower than the previous one. So I can consider this, because this is lower than previous one. Okay, this is lower than previous one, and the test error is also lower than the previous, training error is also lower than the previous one. So this could be a very good model because it is showing less test MSE error. Okay, less test MSE error and less train MSE error. Less train MSE error. So that could be a very good fit. That could be a very good approach. But as we go further to the green model, okay, then it is showing a very different case because we have a very minimum training error. Okay, we have a very minimum training error, but at the opposite, we have a very high testing error, which is a very bad thing because in testing, we want our model to perform well. Even it perform bit high on training error, we want to perform less in the test error. And this is a very bad thing. And you can see the green model, what is trying to do. It is trying to capture every noise, and it is trying to do this, which is causing its error more. Okay. So simply what I can consider, I can consider this blue model more. I can consider this blue model more because it is at a very sweet spot. It is at a very sweet spot in which my training test MSC is very low and train MSC is also low. So I will consider this model. Okay. Don't get greedy as seeing the training error is very low, because it doesn't actually matter that how low your training error is. Until and unless it is not compared to the test error, we cannot get to the conclusion. We cannot simply get to the conclusion. Okay. Now, moving to the next uh, graph, but is same, which is same as this. So in this graph, the data is kind of like this. The data is kind of like this. The relationship it is showing, which means as x is increasing, y is not increasing. It is actually at a certain point. At a certain point, it is declining. Y is declining. Okay, so here we have a different case. So let's see how we handle it, which model we try to fit. Okay, so the very first model that we use is linear model, and we see the yellow model, it terribly fails here because it it is showing a very high error, high training error, high testing error. Okay, now when we go with the blue model, okay, the blue model, so what blue is trying to do here is that this is not blue, man, sorry. So what blue is trying to do here is that blue is like this, which is actually capturing very well because our data is like this. Okay, and blue model, okay, is doing very well at this level. So we can consider this because the test error is also low and the training error is also low. Both are very low. Okay. But on the other hand, we have the green model, which is still terribly failing. Why? Because it is trying to capture every move. Should we consider it? No, absolutely no. Because even if the test error, even if the training error is low, we don't want our test error to be high. We don't want our test error to be high because the training error doesn't just justify our model's accuracy or model's performance. We need both train and train and test error. Okay, and we want the sweet spot where the train error is also low and the test error is also low. Train and test both are low. We want this approach, not just the train error is low and test error is high. This is a very bad way to generalize it. Okay, so if the model is capturing the data pattern, we should go with that model where the test error is low and train error is low, because as the flexibility increases, okay, which means flexibility is increasing, MSC is also increasing. Okay, so as flexibility is increasing, MSC should not increase because it is the performance of our model. And if the performance of our model decreases, the bad it gets. Okay, that simply it was. So we have to take care of, as the flexibility increases, the MSC should not increase. That's why we use different models, different approaches. Okay. Now, bias variance trade-off. One of the most important topic in whole machine learning, the bias and variance. So, what bias is? So, bias is error generated by approximating, okay, error generated by approximating a possibly complicated real life, usually how much and the difference. Okay, so bias is actually the assumption that we make about a model. or the assumption that we make about the data, that is it linear or not. Okay, is it linear or not? Okay, so suppose this is the data. Okay, this is the data and it looks like this, it looks like this. Okay, what it is drawing, it is doing like this. Okay, the data is something like this. Now what we assume is that we assume that the model, the data is linear. Okay, the data is linear, we fit a linear line. Okay, and it terribly gives a very high error because the model is not sorry, the data is not linear, the relationship is not linear. So our bias is very low. Sorry, the bias is very high because uh, okay, yeah, because if our bias is correct, okay, if our bias is correct and error and the error and the error is low, then the bias is low. Okay, but the error is high, then the bias is high bias. Okay, so we made assumption about the data that it is linear, but it was the data linear? No. So we can simply say that it was high bias. Okay, it was high bias because the error is high when we uh, do linear assumption on a data which is curved. Then the error is high, which means high bias. But if we have assumed the data is curved, okay, then our bias would be low. Then our bias would be low because the error is low and our bias was correct. Okay. So bias is simply that how much it differs than we have assumed. Okay. If we have assumed that the data is linear and we fit linear model on it, then our bias was correct, error is low, and the bias is low. But if the data is not, it is curved or it is polynomial or it is clustered, okay, it is a grouped data and we made assumption of linear, then our error is high and our bias is high. Okay, so what variance is actually? Okay, by definition, how much the produced estimate f hat changes when the data set changes. Okay, so our bias, this was our data like this, something like this. We made a bias of linear, our bias was linear. Okay, our bias was low, which means error is low. If error is low, we can say that it captured pattern, and if it has captured the pattern, it can simply generalize new data. And if can capture the new data, it can generalize the new data, the variance. Okay, variance, which says that how much the f estimate changes when the data changes, which means when we give test data, which is another data, and how much f changes, its prediction changes, which means is it giving the same output or not. Okay, same output or not. Okay, in variance. Okay, so a captured pattern, which means new data generalized well, new data generalized well, which means low error, which means low error of test data set, which means as the data set changes, which means as new data come, the error rate will always be low. And as the error rate is low, which means our model is performing and giving the performance at the same level as it was giving earlier. And as it is giving the earlier performance, the variance is very low. The variance is low because the prediction is not changing. It can range between, up or down of 1 or 2 point, 3.5 point. There's a range. Okay. And if the model predicts between that range, we can simply say the variance is low. The variance is low. But does it happen in real life? No, man. It doesn't actually happen in real life. It doesn't actually happen in real life because low error doesn't mean that it has actually captured the pattern. It has actually captured the pattern because low error or zero error could be like this. It also giving us a low error. This new pattern is also giving us the low error. Does it mean that it has captured the pattern? No. And if it has doesn't capture the pattern, how it can generalize well on new data? It cannot. And as it cannot generalize well on the new data, which means the new test MSC's error will be high. The test MSC's performance will be terribly uh, high. The performance, the error will be high. And as the error is high, the variance will be high. The variance will be high because variance changes. Variance tells the data is not generalized well. The new prediction is not getting well. Okay. If the test error is high, the variance is high. And if the if the test error is low, the variance is low. But does variance tells about how well our model is? No. No, it doesn't. Okay. So let me tell you a thing. As general, as general, the more flexible model it is, okay, the more flexible model it is, the lower the biases. Okay, the more flexible model is, the lower biases and variance is high. Which means as the flexibility increases, see man, see, as the flexibility increased, which means is tried to capture all the patterns, which resulted us into a very low error, which resulted us into very low error, which means low error, low bias, low bias. But is it the pattern that we wanted to capture? It has captured? No, absolutely no. How can we say that this is a good model? Because as the flexibility is increasing, as we have seen earlier, as the flexibility increasing, the bias is decreasing and variance is increasing, because if it has no pattern captured, how it can generalize well on new data? It cannot. And this is we have to keep in our mind. This is what we have to keep in our mind. Okay. Which means which low bias and high variance, which you often call as overfitting. Which we often call as overfitting, man. You have heard this term. Overfitting. What happens here is that model is too complex that it tries to capture all data point, even the noises, which should not be captured. That results into very low bias, but it gives very high variance, which is not good thing, which is not a good thing. Okay. Now we have another example. So we are seeing here as the flexibility increasing, okay, the error is actually decreasing. The error is decreasing. There's a total different scenario here because the data is like this and the linear model won't work here. The linear model won't work here. Okay. Why? Why? Because data is not like that, man. Data is in this S shape. Okay. Data is like S shaped. Okay. If you see horizontally, then data is S shaped. Okay. And still, the yellow model, which is the linear model, is not performing very well. The yellow model is not performing very well because the test error is very high and train error is also very high. Train error is also very high because it has not captured the pattern. But as we see different models, okay, the blue model, what is blue model doing? It is actually capturing the data. It is actually capturing the pattern, which results into low train and test error, low train and low test error. Okay. And there is another model which is green model, which we can definitely consider, man, because earlier, uh, earlier it was giving very high test error and very low uh, train error. But here we have very low train and very low test error, which can be considered. So this is our first choice, this is our second choice, and this is our third choice of the model. Okay, you can even see, man, if we put a linear model here, how it can generalize, it cannot. It is actually underfitting. Okay, it is underfitting, which means high bias and low variance. Why low variance? Because the error will be same, because it hasn't even captured a pattern so that it can make even a prediction. If it cannot make a prediction, how it can give us low or very high error? The error always be the same because it has nothing uh, in hand. This is it. Okay. So underfitting in which high bias, high bias and low variance, while overfitting, low bias and high variance. Got it?